Hey everyone, this is going to be a very quick-paced review of Unit 8 because it's been a little while, but at the same time you probably do remember a bit. This in no way replaces the other videos, so I recommend going back and studying those, and this is also going off of the need to know. But this is just sort of a faster version to give you a quick reminder of all the important concepts, but again, it doesn't replace them. So remember, Unit 8 was about gases essentially. So remember we said that there's kinetic theory of matter, right? Kinetics is talking about motion. And so all matter has motion. Even solids we said have motion, they just vibrate in place. The only time matter doesn't have motion is when you're at absolute zero, right? But otherwise all matter, solids, liquid, and gases have motion. And we know that liquids and gases have more motion than solid, for example. So yeah, we call this energy of motion kinetic energy, which we'll revisit in a second. And we know that solids look like this and they're rigid. They vibrate in place. They have a definite volume and a definite shape, right? Liquids do not have a definite shape, right? They take the shape of their container, but they do take up a definite amount of space because the particles are still packed together, just not in order. But the liquid cannot be compressed, right? And a solid cannot be compressed. But a gas can be compressed, and that's what makes it different. And the key reason why it can be compressed is because there's space between the particles. That's not true of liquids or solids. So in gases, there's much more space between the particles, meaning that they can take up much larger containers or much smaller containers, right? That's how we can fit so much gas in little containers, because it can be compressed, and that's what makes a gas different. And this whole thing is talking about gases. That's what this unit is discussing. So gases don't have a definite shape or a definite volume. So solids, definite. Liquids, definite volume but not definite shape. And gases, indefinite shape, indefinite volume. Okay, and then just really quickly, the kinetic model of ideal gases, how we describe ideal gases. First of all, in real life, gases are not ideal, but they behave similarly to ideal gases, and so we can kind of make these assumptions, and most of the time they hold true, so we just make these assumptions. One of them is that there are no attractive forces between the gas particles. That's what makes something ideal. In reality, there actually are attractive forces, but they're so minimal, and they only occur in really specific situations that we just pretend for our purposes that they're not attracted to each other. We also say that they travel fast and in straight lines, sort of like a pool ball, right? Travels fast in a straight line, hits the wall, and then bounces off. And then we also say that their collisions are perfectly elastic, meaning that when they hit the wall, they then bounce off and not lose any energy, which in reality that doesn't really happen with collisions, but we make all these assumptions in order to do calculations, and the calculations hold true enough of the time in most situations, so we just make these assumptions, and that's why we call them ideal gases. But real gases don't behave this way, especially under really cold temperatures and really high pressures. That's when you see that real gases don't follow these properties, but most of the time they do. And so this is what makes a gas most of the time, essentially. These three main principles. No attractive forces, they travel fast and in straight lines, and that they are perfectly elastic collisions. No energy lost in that collision. Okay, so we know that at higher temperature, things tend to move faster, right? So this is showing that a lower average kinetic energy, lower temperature, higher average kinetic energy at a higher temperature. So that we know intuitively. And there are two main scales that we talk about in science and what most of the world uses, Celsius and Kelvin. Celsius was designed around water. So they said, we'll just take the temperature at which water freezes and we'll designate that as 0. Take the temperature at which water boils and we'll call that 100 on the Celsius scale. So remember, this is like entirely man-made. Kelvin is different in that, first of all, you don't use degrees Kelvin, you just say Kelvin. But also Kelvin is it's called the absolute scale. It's based on absolute kinetic energy. Meaning that when you get to 0 degrees Celsius, for example, you're still not as low as you can possibly go in terms of kinetic energy. Particles that are like frozen water, for example, at 0 degrees Celsius, still has kinetic energy. It's just vibrating in place at that point, but there's still energy there. Kelvin is the only temperature scale that actually corresponds with the kinetic energy. So there's still motion associated until you get to 0 Kelvin, essentially. So in other words, you can't have any negatives in Kelvin, because once you get to 0, everything stops. You can't have negative motion. Whereas Celsius is nifty, but it's just based on water. It's not based directly on particle motion the way that Kelvin is. Quick conversion. So in order to get from Celsius to Kelvin, you add 273. And in order to get from Kelvin to Celsius, you subtract 273. Which makes sense. You wouldn't subtract from Celsius to Kelvin because you might then get a negative number, and Kelvin can't be negative. That's one way to remember, but you'll always have these formulas anyway. Temperature, we know, is an average of the particle's kinetic energy. It's based on their average kinetic energy. So this curve is based on the cold drink. Most of the particles are very cold, very slow, and so that's why the hump is higher at the lower energy portion of the x-axis. But we still see some of the particles do have high energy. There's some overlap, and then the red curve represents a hot drink, where we see that most of the particles have much higher kinetic energy. They're further to the right on the x-axis. But there are some particles in cold tea moving with the same kinetic energy as there are with hot tea, because the temperature is based on the average. So that means some particles are above it, some particles are below it, but temperature is based on average. So there is some overlap. Because it's based on the average, there are some particles that are moving very fast in the cold tea, but most of them are not. And there are some particles that are moving very slow in the hot tea, even though most of them are not. And so, again, temperature is based on the average kinetic energy, especially when we're talking about the Kelvin scale, which is more directly related. Speaking of temperature, we said that there's a formula for how we talk about this kinetic energy that we're talking about, this energy of motion. And the formula is 1/2 mv squared. It's listed down here below, where the m stands for mass and the v stands for velocity. So 1/2 the mass times the velocity squared. And so why that's important to us is that, especially when two gas particles are at the same temperature, they're not actually going to be moving at the same velocity. So the same temperature implies that their average kinetic energy is the same, right? Because temperature is related to average kinetic energy. So on average, if you have hydrogen at 300 Kelvin and oxygen also at 300 Kelvin, they're going to have the same equivalent kinetic energy. They're going to have equal values of 1/2 mv squared. However, we know that hydrogen is at a lower mass and oxygen is at a higher mass, which means that their velocities have to adjust accordingly in order to still be equal. So that's kind of shown down here. The oxygen has a higher mass. You can kind of see that the particles are also larger in volume, and therefore oxygen has a lower velocity. And hydrogen has a lower mass, and therefore has a higher velocity to make up for that. Let me also show you just what that looks like. I mean, the key thing here is that the one with the lower mass moves faster. That's the main concept. But we're basing it on this kinetic energy formula and the fact that temperature is directly related to kinetic energy. So let me show you what that looks like. So first of all, just so we can directly compare, we're going to be looking at, in a second, neon versus argon. We know that neon has a mass of 20.18 on average is the average atomic mass, and argon's average atomic mass is 39.948. So argon is the more massive one. Okay, so keeping that in mind. Okay, now here is our direct comparison. So both of these gases, on the left is argon, remember the more massive one, and on the right is neon. Both of these gases are at the same temperature in Kelvin. They're both at 100 Kelvin right now. So they're both at the same temperature. So that means they both have the same average kinetic energy. However, because argon has a larger mass, it makes up for that by having a lower velocity. See, these particles are moving more slowly. And because neon has a lower mass, it makes up for that by moving faster in order for them to have equal 1/2 mv squared values for kinetic energy. So that's what we're talking about with that. Okay, also very quickly, we said that there's pressure on all of us right now. Right now as you're watching this video, there's pressure on you. It's the pressure of the atmosphere, the pressure of the air above you. And so it's gas pressure. The pressure is more as you're lower on towards sea level, and there's less pressure as you move higher in altitude. So that's why your ears pop going up or down a hill, because of the change in pressure. we said that atmospheric pressure is equal to 101.3 kPa, which is the same as 760 millimeters mercury, which is the same as 1 atmosphere, which is the same as 14.7 pounds per square inch, or psi. All of these are equivalent values. You do need to be able to convert between these. So in order to convert, you take what's given. So if we're trying to convert 17.6 psi to kPa, for example, 17.6 psi times, put the same units on bottom, and then the units we're trying to get to on top, and then we need to use equivalent values. So 14.7 is equal to 101.3 kPa, so that's why we're allowed to use this. So our units cancel, and again, in order to do this math, we multiply across the top, so 17.6 times 101.3 divided by 14.7 gets you your answer. So the rules are that the units need to cancel, and that for your fraction, the top needs to be equal to the bottom in some way. So you do need to be able to do those conversions for this upcoming quiz. Okay, just very quickly, we talked about the number of particles. Particles are directly proportional to pressure. So if you have double the particles, you have double the pressure. Gas pressure and volume. Boyle's law says that pressure and volume are inversely related. They're inversely proportional. So if you have half the volume divided by 2 the volume, you have double the pressure, and vice versa. So they do the opposites. Your graph for Boyle's law looks like this. It's a curve where as you go down in pressure, you're going up in volume. As you go down in volume, you're going up in pressure. So an inverse graph looks like this. That's Boyle's law. Here we're seeing that again. It's the Boyle's law graph. Charles' law. Charles' law is based on volume and temperature. This is what the graph of it looks like. Volume and temperature are directly proportional, so as one goes up, the other one also goes up. As one goes down, the other goes down. So as you move to the right, as temperature is climbing, particularly in Kelvin, is what you need to use for all these gas laws, then the volume also goes up. So as temperature goes up, volume goes up, so it looks like a straight line, essentially. Okay, volume and temperature, again, we see that as it gets hotter, the volume grows in this balloon. As it gets colder, the volume goes down. So they both go up together, both go down together. Here is Charles' law, and again, it always has to be done in Kelvin. Temperature and pressure are directly proportional as well. So it has to be in Kelvin, and as the temperature in Kelvin is doubled, the pressure is also proportionally doubled. The combined gas law, and all the previous gas laws only work if you keep everything else constant except for the 2 variables you're looking at. The combined gas law allows you to compare pressure, volume, and temperature all at once, as long as you keep everything else constant. The ideal gas law allows us to really take stock of all of these variables. Remember, P is for pressure, V is for volume, N is for the number of particles, which is really the moles. R is a constant that never changes. It's a number you put in to help do the calculation. And T is for temperature, and that's always in Kelvin. So how do we use this ideal gas law? Well, we think of it, they need to be equal, right? PV needs to be equal to nRT. So if we look at, for example, if the pressure goes up, what will happen to the volume? In order to balance the scales again, the volume needs to shrink. So if 2 variables are on the same side of this equation, they have to do the opposite of each other. So pressure and volume do the opposite. Pressure goes up, volume goes down. We already said that in Boyle's law, they're inversely proportional as long as everything else is held constant. It's the only time you're allowed to do that. If temperature goes up while holding all else constant, what happens to the volume? So if our T goes up, that means that our V, in order to balance things, must also go up, which we said is Charles' law, right? As long as everything else is held constant, that means that things that are on the opposite side of the equation have to do the same thing as each other. So if we rewind really quick, things that are on the opposite side are directly proportional to each other. Double one, you must double the other. Things that are on opposite sides are directly proportional to each other. You double one, you must double the other. Things that are on the same side do the opposite. So P and V do the opposite. Really, honestly, the only things that are different are P and V. Everything else does the same thing. P and T do the same thing. Number of particles in P do the same thing. T and V do the same thing. It's all related. The only ones that's different that we need to be aware of is pressure and volume do opposites. So that's again our quick crash course of the unit. Hopefully that was helpful. Feel free to rewatch, but again, it doesn't replace anything. It just helps you get the juices flowing remembering this unit. Please let us know if you need any help with anything before the test. Thanks. Oh, and remember, chemistry is everywhere.